In this lesson, we will discuss how to compute complex roots. In the previous lesson, we saw that writing complex numbers in exponential form was a very useful way to understand multiplication of complex numbers. In this lesson, we will use the exponential form of complex numbers to help us compute the nth roots of complex numbers. So first, let's define the nth root of a complex number. An nth root of a non-zero complex number z0 is a non-zero number z such that z raised to the power n equals z0. So let's look at two complex numbers. Suppose we have two complex numbers z1 and z2. I'm going to write z1 in exponential form as r1 e to the I theta 1 and z2 as r2 e to the I theta 2. Then these two complex numbers will be equal if they have the same radius. So it'll be equal if and only if r1 equals r2, so they have the same modulus or same absolute value, and their arguments, theta 1 and theta 2, differ by an integer multiple of 2 pi. So theta 1 would have to equal theta 2 up to a multiple of 2 pi. So plus 2 pi k for some integer k. So the idea is I want to look at the equation z to the n equals z0. So suppose z to the n equals z0, where I'm going to write z as r e to the I theta, and z0 I'm going to write as r0 e to the I theta 0. Then from my previous statement saying that z to the n equals z0, we get that r e to the I theta to the power n equals r0 e to the I theta 0. Which implies that r to the n e to the I n theta equals r0 e to the I theta 0. And we now know that their absolute values must be the same, so r to the n and r to the nth power must equal r0, and the argument n theta must equal theta 0 plus an integer multiple of 2 pi. So then r must equal the nth root of the positive real number r0, and we see that theta equals theta 0 plus 2 pi k over n for some integer k. So we see that there's going to be multiple ways to represent the argument theta for the nth root of z0. This leads to the definition of the set of the nth roots of z0. So the set of nth roots of z0, which is r0 e to the I theta 0, in set form, we're going to write this as z0 to the 1 over n power for the nth roots of z0. So it's the set of all expressions equal to the nth root of r0 times the exponential e to the I times the quantity theta 0 plus 2 pi k all over n, where k is an integer. A few facts about nth roots. There are, in fact, n distinct nth roots of any non-zero complex number z0. And since they all have the same modulus or absolute value, they will all lie on the circle centered about the origin with radius nth root of r0. And if you look at the arguments of these nth roots, they'll each differ by 2 pi k over n. So they're actually equally spaced around this circle. Every 2 pi over n radians, starting with theta 0 over n. So the n distinct nth roots of z0 are the following set. The nth roots of z0 would be the set which is the same as the set above, but now k runs from just 0, 1, 2, up to n minus 1. So when theta of 0 is equal to the principal value of the argument of z0, then the nth root of z0, the nth root of r0 e to the I theta 0 over n is called the principal nth root. Of z0. So let's look at an example of the set of nth roots of a complex number. Suppose I want to solve the polynomial equation z to the fourth minus 16 equals 0. Well, this equation is equivalent to z to the fourth equals 16, and essentially we're finding the fourth roots of 16. So we need to find the fourth roots of 16. So the solution to this equation will be when z is equal to the fourth root of the real number 16 times e to the power I times a quantity. Well, the principal argument of the real number 16 would be 0, so it would be 0 plus 2 pi k all over 4 for k equals 0, 1, 2, and 3. So this just simplifies to, well, the fourth root of 16 is 2, so z equals 2 e to the I pi k over 2 for k equals 0, 1, 2, and 3. So the fourth roots of 16 are elements of the set 2 e to the 0, 2 e to the pi I over 2, 2 e to the pi I, and 2 e to the 3 pi I over 2. So 2 e to the 0 is 2. 2 e to the pi I over 2 would be 2i. E to the pi I over 2 is I. E to the pi I is negative 1, so that would be negative 2. Then e to the 3 pi I over 2 is negative I, so it would be negative 2i for the last root. And so just to illustrate the fact that these roots all lie on the circle and they're equally spaced, they'll be all centered at the circle with radius 2, centered at the origin. So we have 2, 2i, minus 2, and minus 2i. We see they are all equally spaced around the circle centered at the origin with radius 2. These would be the fourth roots of 16. Next, we'll take a look at roots of unity. That is, nth roots of the complex number 1. So the nth roots of 1 satisfy z to the n equals 1. So we know the real number 1 will always be an nth root of 1, but we know now that there are going to be n complex numbers that satisfy z to the n equals 1. So the nth roots of 1 will be equal to the nth root of 1 times e to the power I times a quantity 0 plus 2 pi k over n. Again, because the principal argument of 1 is 0. So this just simplifies to e to the power 2 pi I k over n for k equals 0, 1, up to n minus 1. So we can list the set of roots, nth roots of unity as the set when k equals 0. This just simplifies to the number 1. And then we get e to the 2 pi I over n, e to the 4 pi I over n, all the way up to e to the 2 pi I times n minus 1 all over n. And these roots of unity are typically written as powers of omega n, where omega n is the primitive nth root of unity. So I'm going to write omega n as e to the 2 pi I over n, and this is called the primitive nth root of unity. Then the set of roots of unity becomes 1 omega n squared all the way out to omega n to the power n minus 1. So let's look at the cube roots of 1. So it's going to be 1 e to the 2 pi I over 3 and e to the 4 pi I over 3. If we write this in rectangular coordinates, we'll see that these are the points. The complex number is 1. Then cosine of 2 pi over 3 plus I sine of 2 pi over 3. We can write that as minus 1/2 plus I square root of 3 over 2. And then the third root of unity would be negative 1/2 minus I radical 3 over 2. Let's take a look at these roots of unity in the complex plane. So here's the unit circle. We have the root 1, the root negative 1/2 plus I radical 3 over 2, this point over here. And then the third root of unity would be down here. This would be the point negative 1/2 comma negative radical 3 over 2. We'll see that these points are equally spaced around the unit circle, and in fact that these 3 points form the vertices of a regular triangle. So we can further investigate this idea of roots of unity in the complex plane using the website desmos.com. So I just searched for roots of unity in Google and found this following example from desmos.com. So you see the polar representation of the complex plane, and we can put the circle with radius 1 on this coordinate plane. So we see it highlighted and identified by this green dotted line. So this would be the unit circle. And I've let n equal 2. So let's look at the square roots of 1. I'm going to add to this graph. The square roots of 1 are just 1 and negative 1. If I change the n, we can look at here are the cube roots of 1 that we just identified in the previous example. Fourth roots of 1, fifth roots of 1, sixth roots, and so on, all the way up to n equals 12. And again, it's neat because it illustrates the fact that all these roots of unity are equally spaced on the unit circle. We can also look at the lines connecting these 3 points. So let's look at these lines, and we can see that the lines joining these roots of unity form the vertices of regular polygons. 4, 5, 6, 7, 8, 9, 10, 11, 12. You can type in the address listed up here in the bar, and you can investigate roots of unity using this application.